Yeah, in the last module, we just had a brief introduction to heat transfer in radial systems. So, we will go through this in detail now. So, radial systems with typically we will look at cylinder and no volumetric heat generation. So, if I go and a cylindrical coordinate system typically is this. This is your r direction, this is my theta direction and this is my z direction. So, r theta z coordinate system, r theta z. Okay, this is what will be your cylindrical coordinate system. So, the general heat diffusion equation which we will not derive here, but those of you who are interested, for the Cartesian coordinate we had derived this here as a part of the class. For a cylindrical coordinate system, this is be your control volume of interest. Please remember, each as I move away from the center of the circle, the area for heat transfer. So, if I call this A, B, C and D and this is E, F, G, H, area A, B, C, D, which is the arc in this part, I am shading this one and this one I am shading it vertical like this, is smaller than E, F, G, H, because R at A, B, C, D is smaller than R at E, F, G, H. It is a larger arc of the same circle because the radius associated with it is going to be different. So, this aspect is going to be involved in the derivation of the energy or heat equation. This is R direction, this is Z direction and this is theta direction. So, this is d theta, this is R, this is R plus dr, this is dz. Okay. So, you will write various areas, area A, B, F, E is equal to area C, G, H, D is equal to dr into dz. This will be like a rectangle. Then similarly, you would have heat transfer from the bottom to the top. So, you will write area AEHF is equal to area BFGC, which is nothing but R d theta plus R plus dr d theta by 2 into this is this arc length plus this arc length by 2. So, we are taking an average thing times dr and you neglect the higher order terms. So, it will come out to be a simple one and of course, you have area ABCD is equal to R d theta, which is this one, into dz, area EFGH is equal to R plus dr d theta into dz. That is all is the difficult part in the derivation in cylindrical coordinates. Then you go back and write E dot in minus E dot out plus E dot generated is equal to E dot stored. dV for this control volume is R dr d theta dz. This is standard. So, QR plus Q theta plus QZ is E in minus QR plus DQR by dr plus q theta plus dq theta by d theta plus something for the z plus q triple prime or q dot r dr d theta dz is equal to rho r dr d theta dz Cp dt by dt. So, this is your setting up of the diffusion equation, and once you go through the maths, which we are not going to derive here, we will get the energy equation in cylindrical coordinates is 1 by r d by dr of k r dt by dr plus 1 by r square d by d theta of k dt by d theta plus d by dz of k dt by dz plus q dot is equal to rho Cp dt by dt. This is your three dimensional unsteady heat conduction or heat diffusion equation in cylindrical coordinates, and I have shown you the procedure. Those of you who are interested can go and try to derive this. The only catch here is this r will not come out of the derivative, and therefore, when you divide through by this term as you did in the Cartesian coordinate, the r's will not cancel and this r will, this what you are dividing will remain here as 1 by r. Same thing here, because d theta has units of radians, does not have the unit of length. So, it is always r d theta, r d theta. So, keep that in mind. Anyway, if I look at now one dimensional in radial direction with no volumetric heat generation. So, this goes to 0, steady state this goes to 0, 1d in r direction. So, these two go to 0. I am left with 1 by r d by dr of k r dt by dr is equal to 0, which I will now write in terms of regular derivative. K can come out. So, it will be 1 by r d by dr of r dt by dr. Please remember, this r is what makes your life very difficult. This r is a variable which is a function of the radial coordinate. You cannot take it out. That is what is taking care of the fact that as my radius increases, the area available for heat transfer increases. This term has come from the surface area available for heat transfer. That is the implication or where it has come from, because these I will use Fourier's law, right. So, minus k a r d by dt of dr minus k a theta d by dt of d theta, and that is what this r remains. Now, if I look at this thing here in your set of slides, this is what is the equation that is the remaining. So, this equation now I am going to do for a hollow sphere. Why hollow sphere? Because we would like to develop the expression for conduction resistance across a hollow sphere. So, we have we have a hollow sphere of inner radius r1, outer radius r2, okay, and the thermal conductivity of the material is K. The inside surface is at Ts1, outside surface is at Ts2. This is a classic case of hot fluid being transported through the pipe. Wall has a particular thickness. So, the inside wall is hotter, outside wall which is exposed to ambient air could be cooler. So, we are looking at now a typical one dimensional radial heat conduction problem, where I have, if I just draw this pipe like this for you, I am just taking a cut section somewhere. This is your center line, this is the fluid, this is the wall. This is Ts1, this is Ts2. Okay, the flow is coming in this way and heat is supposed to go out this way, right, a classic problem. So, convection inside H T infinity 1 or T infinity I, let me not mess up with the nomenclature. So, H1 T infinity 1, H2 T infinity 2. So, H1 T infinity 1, this is H2 T infinity 2. So, H1 T infinity 1, H2 T infinity 2. So, again like conduction, we have three resistances, one for the outside convection, one for the conduction in the wall, one for the convection inside. So, T infinity 1 to T infinity 2 are convection outside, are convection inside, are conduction at the wall. Three resistances, we want to find out what this is. This is nothing but 1 over H naught A naught. This is 1 over Hi or H1 A1. So H2 A2, whatever. H2 A2. This is 1 over H1 A1, inside or outside, whatever. But please bear in mind, whichever nomenclature you are using, please bear in mind, this is not the same. In plane wall, inside and outside surface areas were the same. You just had the same area for heat transfer. Whereas here, this is 2 pi R2L, this is 2 pi R1L, and that is where the areas change, the resistances change. You cannot have the same area, and the fact that the area, surface area for heat transfer changes radially will also come in this R conduction, which we will see very shortly. So, let us just go back to the slides, and QR is the heat transfer rate in watts, which is minus Ka dt by dr, which is nothing but minus K into 2 pi RL dt by dr. So, this 2 pi RL is the surface area at any radial location, which is normal to the direction of heat transfer. So, heat flux is K dt by dr, heat transfer rate is Ka dt by dr. Point to note, point to remember, very important point to remember, QR is minus Ka dt by dr. This is constant. Q double prime, which is QR by surface area, is minus K dt by dr, is not constant, is a function of R. Always, because this is a function of R. Very important concept in radial systems. Heat flux is not a constant. Heat flux depends on the area available for heat transfer, which is the surface area, and therefore Q, whereas in plane wall Q is constant, steady state, Q double prime is Q divided by A surface is also constant. Both these are constant, whereas here only heat transfer rate is constant, heat flux is not a constant. Please remember this, carry this home with you. It is not going to be a constant heat flux. That is a very important concept that you need to be aware of. Okay. So, the next part, next slide, we are now just going to integrate this to get whatever we need, and I will just show that to you in the differential equation. 1 by r d by dr of r dt by dr equal to 0. So, integrate this. So, d by dr of r dt by dr equal to 0. First integration would give me r dt by dr is equal to C1, implies dt by dr is equal to C1 by r. Integrate again, T of r is equal to C1 log r plus C2. Two conditions needed. So, at r equal to r1, T is equal to T1 or Ts1, at r equal to r2, T is equal to Ts2. Use this here. Ts1 is equal to C1 log r1 plus C2. Ts2 is equal to C2 log R2 plus C2. Two equations, two unknowns C1 and C2. It's just a matter of substitution. So, I am saying Ts1 greater than Ts2. So Q is going from inside to outside, which means Ts1 larger, I will subtract Ts1 minus Ts2 is equal to C1 log of R1 minus log R2 is log of R1 by R2. Please remember, R1 is smaller than R2, so this log term will be negative. So whatever we do, C1 is equal to Ts2 minus Ts1 divided by log R2 by R1, or you will write Ts1 minus Ts2 divided by log R1 by R2. Whichever way you want to write, you write, but please make sure whatever is the first term coming in here, if this is 2, this also needs to be 2. If this is 1, this needs to be 1. The signs, everything will take care of itself. I substitute for C1 here, and then I will be able to get, not here, I will substitute for C1 in any of these, either this or this, whichever I want, I will get C2, and that is what is shown in the slides here. So C1 and C2 have been obtained. C1 and C2, therefore, when I put together to get my heat transfer rate, if I have to get my temperature distribution, I get T is equal to Ts1 minus Ts2 divided by log of R1 by R2, log of R1 by R2 times log R. This is the solution. The solution was C1 log R plus C2. Solution is right here on top. C1 log R plus R2. C1 is being substituted, C2 is being substituted. Ts1, Ts2 log R1 by R2 is a constant. So this is a number. Ts2 is a constant, a number. This whole thing is a constant, which is because all are S1, S2, R1, R2. The variable of interest is R, and the dependent variable is T, which is again what we are interested in. So if we just go back here, T1, T2, everything is known. T of R therefore is Ts1 minus Ts2 log of R by R2 divided by this one. So this is a compact form of the temperature distribution, and unlike my plane wall, it is not very simple. Okay, it's not very simple, but the heat transfer rate is minus K into 2 pi RL dt by dr. dt by dr is now from here. Where is dt by dr? I had calculated dt by dr in this step, C1 by R, right here, C1 by R. I have now the value of C1. So Ts1 minus Ts2 divided by log R1 by R2 whole divided by R. That is what is here. C1 by R is substituted for dt by dr, and you group this together in a form which I like. What is it? Q is equal to delta T divided by everything else. Now, everything else will have log of R2 by R1 and 2 pi Lk. Everything else should be that. That is what I have put here. Log of R2 by R1 into 2 pi Lk. So, once you write this, RT conduction will come out to be this. Let me just show that to you instead of talking around here. So I would get Q is equal to minus Ka dt by dr, which is nothing but minus K into 2 pi RL into Ts1 minus Ts2 divided by log of R1 by R2. R2 by R1, R1 by R2. So this would give me Ts1 minus Ts2 divided by log of R1 by R2 with a minus sign divided by 2 pi Lk, which is Ts1 minus Ts2 divided by log of R2 by R1 divided by 2 pi Lk. And what did I tell? If I am able to write Q is equal to delta T by everything else, that everything else is my resistance, correct? So now, keeping the same definition in mind, this quantity is my conduction resistance for a hollow cylinder. And please see this carefully. It was R1 by R2. It was a small number by large number, negative. The minus sign took care of it. And this is now a positive quantity. Ts1 greater than Ts2. So, this is greater than 0. This also is greater than 0. So, what you need to remember, R conduction in a cylinder, log of R2 by R1 divided by 2 pi Lk. If I write it this way, the temperature difference on top should be the larger minus smaller. Keep this in mind, larger minus smaller, and this will be larger by smaller. So, do not go with the subscripts 1 and 2, you will make a mistake. This is the magnitude now because the negative sign has been absorbed here. So, R outer divided by R inner you want to call, that is also fine, log of that divided by 2 pi Lk, which is R conduction cylinder. Okay. So, this is something which you need to commit to memory, conduction resistance in a cylinder. Okay. So, we will take a look at what is there next. So, Q double prime, which is the heat flux, which is QR by 2 pi RL, which is just going to be K by R Ts1 minus Ts2 divided by log of R2 by R1, and this R's will get cancelled. So, you just are going to be heat flux, which is going to be independent of R, the R will get cancelled. Okay. So, now we have the same concept of resistances in series. So, I have a hot water pipe, I cannot put a single insulation, I have multiple insulations. Okay, what is going to be the case? It is just the same problem as we had in a plain wall, only big difference. Unlike a plain wall, the resistances still will add, but they are not simple in nature. What else is important here? If you look at this temperature distribution, this temperature distribution is not linear, this is logarithmic. Log of R function is there. Everything else is a constant. Ts1 minus Ts2 divided by log R1 by R2 is a constant. Oops, Ts1 by Ts2 divided by log of R1 by R2 is a constant. You also have log R2 in the denominator, in the here 1 by R2, which is a number. Everything is a constant. Tr is basically a function of log R. So, logarithmic variation in plain wall, it was a linear variation, no heat generation rate. This is logarithmic variation. That is important. The resistances are also complicated, but it is okay, it is not a big deal. The concept of adding the resistances still remain the same. So, if you take a look at this problem, where it is a representative typical problem, convection on the inside and 3 conduction resistances. Here you have an convection on the outside. So, you will write Q is maximum temperature difference divided by the resistances that are there in the path. Maximum temperature difference is T infinity 1 minus T infinity 4. I have 3 conduction resistances 1, 2 and 3. I have 2 conduction resistances, one on the inside and the outside. So, I have 5 resistances. What do I need to care about? H1A1, A1 is 2 pi R1L. A4 is 2 pi R4L into H4, and then 3 conduction here, log of R2 by R1 divided by 2 pi Lka, log of R3 by R2 divided by 2 pi Lkb, log of R4 by R3 divided by 2 pi Lkc. It is just an extension of this. Log of bigger radius by small radius divided by 2 pi Lk of that medium. Same thing. Log of bigger radius by small radius, log of bigger radius by small radius, bigger radius by small radius. 2 pi Lka B C. So, when I put all this, this is QR is T infinity 1 minus T infinity 4 divided by summation of the resistances. Now, I will call this as T infinity, my HA delta T is a form which is very simple. Okay. So, I will call, I want to write this in a similar manner. is UA into delta T. It is just a group of terms. The group of terms is called as UA. What is this group of terms? It is nothing but the group of terms is summation of the resistances, which is 1 over 1 by 2 pi r1 L log r2 by r1 by 2 pi lka log r3 by r2 divided by 2 pi lkb log r4 by r3 divided by 2k lkc plus this one. This is called as the overall heat transfer coefficient. U is the overall heat transfer coefficient. Please remember, we are writing this group of terms which is 1 over summation of resistances for a given system. Okay, I have a system. It's a pipe which is carrying fluid. The water is at a particular temperature, and the walls have particular thickness. The conductivities are so on and so forth. Everything is known. So, given problem, given H values, U is a constant. UA is a constant. Why? Because summation of RT is a constant. Everything here is a number. Everything here is a number, and once I fix H1, Ka, Kb, Kc, R1, R2, R3, R4, H4, this is all a constant. So, one thing which I need to remember is, given system, if all the dimensions are fixed and the heat transfer coefficients are fixed, the total thermal resistance is a constant. So, reciprocal of a thermal resistance, which is U times A, is also a constant. So, for a given system with predefined conditions of flow and geometry, the thermal resistance is a constant, which means U times A. The product of UA is a constant. I am not saying U is a constant. The product of U times A is a constant. This U can be defined in terms of any area that you like: U1 A1, U2 A2, U3 A3, U4 A4. So, it is like 100 is 25 times 4, 20 times 5, 10 times 10, whatever you want. So, we will always say U is defined in terms of a particular area. So, when you see UA, it is fine, it is a number which is reciprocal of thermal resistance summation. But if U alone is given, it has to always be accompanied by the statement based on. U defined in terms of the inside surface area, U defined in terms of the outside surface area, U based on the inside surface area, U based on the outside surface area. So, U1 2 pi R1 L is a constant, which means because R1 is small, U1 will be larger compared to when it is defined in terms of A4, which is 2 pi R4L. R4 is larger, so U4 will end up being smaller because product UA is equal to constant. So, UA is a constant while U is not a constant for a radial system. Again, this is because radius is playing a very important role in defining the surface area. So, if I just want to simplify and define U in terms of the inside area, I will have U into 2 pi R1 L. I divide through by that, I will get 1 by H1 and a bunch of terms where this 2 pi's will get cancelled, R by K log R2 by R1, R1 by KB log R3 by R2, so on and so forth. I could write this U defined in terms of outside area. The expression will have a similar form, but the values of U that you calculate based on inside and outside surface area will be different, because here you will have 1 by H4 will be standing alone, H1 will be standing with respect to R4. So, R4 by R1 H1, whereas here it would be 1 by H1. So, you can take this as an exercise and try to define U in terms of any surface area of relevance in the problem. It could be an intermediate area also, why not? So, U defined in terms of R3, you will get a funny looking expression, more complicated, but please remember everything R1, R2, R3, R4, H1, H4, everything is a number. So, when you put it in, these are all going to be different numbers. How does it matter whether it is 55 or 52? It is a number. So, you divide by a particular quantity, you will get a particular overall heat transfer coefficient. The units of overall heat transfer coefficient is watt per meter squared Kelvin, just like your H value. The point to note again I am saying is U alone has no meaning. U alone has to be always defined in terms of a particular surface area of interest. UA is a constant for a given system where the flow characteristics are set, where the geometry is set. So, UA is nothing but reciprocal of the summation of the thermal resistance. I am not saying conduction resistance, thermal resistances, which includes conduction, convection, radiation, all kinds. So, whether it is series, parallel, does not matter. You find an R equivalent, 1 over R equivalent is U times A, which is a constant given everything else is a constant. UA is U1 A1 equal to U2 A2 equal to U3 A3, U4 A4, etc. Okay. Thank you so much.